Hello and welcome to the handouts for Chapter 4 discussing probability. We're going to be reviewing, and when we do that I'm going to be going a little bit quicker. This is our second, or in some cases third, look at some ideas. I'm also going to be talking about some new questions, so be on the lookout for that. We're going to be using the formulas that we've got to solve for a specified part of it, and in fact in one case we're going to have to do that twice. This first question comes from the deck of playing cards. You've also got this in your workbook, so if you want to open the workbook to that page, let's scroll down and get started. The first question asks, what's the probability of getting a heart? The hearts are 1/4 of the deck, so the probability 1/4. The second question asks, what's the probability of drawing a 5? The 5s are 1/13 of the deck. A queen also 1/13. And a club, just like the hearts themselves, 1/4. Now if I ask what's the probability of drawing a club or a heart, well, that's the probability of drawing a club, 1/4, and another 4th for a heart, for a total of 1/2. Notice that a card can't be a club and a heart simultaneously, so we don't have any overlap that we have to subtract. A jack and an 8 is a very similar question. There's no overlap. These are mutually exclusive. So that means that the chance of drawing a jack, 1/13, the chance of drawing an 8, 1/13, for a total of 2/13. And remember why that is. That's true because the probability of drawing a club and a heart, there is no card that's a club and a heart, is 0, just like there's no card that's simultaneously a jack and an 8. This is not two cards in order. That would look the same, but the question leading up to it would be different. The probability of pulling a black card, well, just like the reds, half the deck is black. And an even card, well, you go through and you count the evens, and you figure out how many there are. So 2, 4, 6, 8, 10. So we count 4 of the 13ths. When two events are mutually exclusive, we can simply find the probability of one or the other by adding the 2 up. And that's true because the probability of them happening at the same time is 0. So really, when we say mutually exclusive, we're saying that the probability of both events happening at the same time is 0. So one in words and one in symbols. Now let's look at a similar situation. The probability of a club or a 6. Well, a playing card can be a club and a 6 at the same time. These events are not mutually exclusive. Notice that we're now going to summarize this at the bottom down here and look at what happens when two events are not mutually exclusive. So you might say, well, what's the probability of being a club? There are 13 clubs out of 52 cards, or, so we're equally happy, so we add the probability of being a 6. There are 4 6s in the deck out of 52. The problem is there's also the 6 of clubs, so we have to subtract that card that we counted twice. 13 clubs, 4 6s, but 1 6 of clubs, which we subtract as 1/52nd. That leaves us with 16 52nds, which simplifies to 4/13. Now notice that a jack or a spade is a very similar situation. The probability of pulling a jack, there are 4 of them out of the deck of 52 cards. There are 13 spades, and we're happy with either, so we'll add. But we'd have to subtract that overlap. The jack of spades is both a jack and a spade, so we've counted it twice. To only count it once, we have to get rid of that overlap. And like before, that gives us 16 52nds, which simplifies to 4/13. And that happens because when we ask the AND questions, what's the probability that something and something else can happen, we don't get 0. You can have a 6 of clubs. In fact, there's one of those in the deck. Similarly, you can have a jack of spades. There's one of those in the deck. You can have a diamond and an ace. That's called the ace of diamonds. And there are lots of even cards that are black. In fact, there are 10 in the entire deck, so that simplifies to 5/26. When two events are not mutually exclusive, they can happen together. So when we're interested in knowing what the probability is of one or the other, we have to subtract that overlap. And similarly, that means that because we have to subtract the overlap, the probability of A and B, that means that it is not 0. And the next thing we're going to look at is conditional probability, and we're going to do that from a table. So suppose that the outcome is already known to have a given characteristic. So the definition of a conditional probability question can be defined in terms of simply counting up the number of ways that different things happen. So in other words, this is a different look at conditional probability. Notice that our numerators and our denominator isn't a probability in itself, it's a sum. In other words, how many have that particular characteristic. So we're going to use this table to answer a question. The probability of A given B. So here we're going to somehow select politicians at random from these two states and from the two chambers. And suppose that you're given that the person is Nevadan. We already know that. Given that a Nevadan was selected, what is the probability that the Nevadan is a senator? So to answer this question, we only consider the Nevadans. So scrolling back up, we're only looking at the Nevadan column, these 5 folks. The 2 senators, each state has 2 senators regardless of its size. Each state has a congressional representative regardless of its size. And then beyond that is based on population. So Nevada is a very small state, certainly much smaller than California, with only 3 congressional representatives. We're only considering Nevadans. There are 5, 2 senators and 3 representatives. We can write this as the probability of selecting a senator given a Nevadan. And this is read the probability of selecting a senator given a Nevadan. We write that in terms of what we're interested in, and we look out for the probability. So given a Nevadan means that we're only interested in the 5 folks who are from Nevada, and of those 2 are senators. So here's that table again, and we're going to go through and ask a bunch of questions for it. The probability of being from California, notice that this is not a conditional probability question. So the denominator will start out as 60, and I see that there are a total of 55 Californians. So this works out to 55 60ths, which simplifies to 11 12ths. Probability of being a Nevadan, similarly, the denominator will be 60. We're not given any information. There are 5 representatives, federal representatives from Nevada. 5 out of 60 simplifies to 1/12. What's the probability of being a Californian or a senator? So we're talking about the 55 Californians, the 4 senators, but then of course we have the problem that there is an overlap. We're counting the 2 senators from California twice. So let's take a look at this. There are 55 Californians, so the probability is 55 60ths. There are 4 senators, so 4 60ths. But the problem is we've counted the 2 from California twice as Californians as in senators, so we have to subtract that 2 60ths. That gives us 57 60ths, which simplifies to 19 20ths. What's the probability of having a Nevadan or a representative? Again, these overlap, so we have to ask the question, well, what's the probability of getting one of the 5 Nevadans? Well, there's 5 out of 60. What's the probability of getting a representative? There's 56 out of 60. But of course the problem here is that we have counted the 2 congressional representatives from Nevada twice, so we have to subtract them, so we're only counting them once. When we do that, we get 58 60ths, which simplifies to 29 30ths. The probability of being a Nevadan and a senator. For this question, we're only looking at the 2 senators from Nevada. So once we see that that and tells us not to look for totals, but to look inside the table, we're seeing that this question asks us what is 2 60ths when we simplify it, and that is 1/30th. A Californian and a representative. There are 53 representatives from California out of that total of 60. Now our first question, similar to the previous page, a given probability. It says that we're given a senator. So in this case, we're only looking at the senators. So the 4 senators from California and Nevada. So the denominator is going to be 4. And of course, just like every state, Nevada has 2 senators. So 2/4 becomes a half. If I tell you that it's a senator and it's one of 2 states, California and Nevada, then there's half a chance that it's from one of those states and not the other. What's the probability that it's that we randomly select a Californian, knowing that we have a senator. Well, the exact same thing. The number of senators from California is the same as the number of senators from Nevada. It doesn't have anything to do with population, the number of voters, the number of citizens, or anything like that. The probability that we select a senator given that that person is Nevadan. So now we're looking at just the folks from Nevada, so that's 5 federal representatives from Nevada. Of that, 2 of them are senators, so this question is going to be 2/5. Now the question, this last conditional probability question, what's the probability that we randomly select a senator given that we have a Californian? So we'll scoot that over, and we're talking about the 55 Californians, of which 2 of them are senators, so 2 out of that 55. We're now returning to the context of selecting playing cards. One of the nice things, the reason that teachers do this is because many times a single setting has lots of different ways you could do that. And in fact here, this same setting is very different than what we saw on the first page, because we're going to draw 2 cards. So now we're talking about the fact that we could draw a jack and then a 9, say. Because we're not talking about the same card. We're talking about 2 cards with replacement. So this time when we're using the word and, we could just as easily be saying then. And if that helps you, that's perfectly fine. There's nothing wrong, to my way of thinking, of writing this as the probability of an ace, then a 9. It means that we're using different notation, and that's got to be a good thing when we're talking about a different situation. That said, the correct mathematical notation, the correct notation in probability is just to use an and be very clear on the context that you're in. So here we're talking about drawing an ace and then a 9. So of course there are 13 in each deck. There are 4 aces. Let's simplify that to 1/13. There is also 1/13 chance of pulling a 9 in the second pull, because we've returned the ace. So there's still 52 cards in the deck. So that simplifies to 1/13 as well. That asterisk symbol means to multiply. I'm using that to match what Kate does in the book. 13 times 13 is 169. The probability of pulling an ace, replacing it, and then pulling a 9 is 1 out of 169 tries. The probability of a diamond and then a club. So first off, the probability of pulling a diamond is 1/4. 1/4 of the deck is diamonds. We return that diamond, so we still have a full deck. We can use the simplified forms and say that 1/4 of the deck is clubs. We're multiplying because of the word and there, and that gives us, well, 4 times 4 is 16, 1/16. A club and then a heart, well, that's exactly the situation we just looked at. A jack and then an 8, well, that's like the ace and then the 9. An ace and then an ace, and you might say, well, what does that mean? That means we pull one of the 4 aces, we put it back, so there are still 4 aces in the deck, and then we pull out another ace. So 1/13 of the deck is aces, and then after we return that first data, 13 of the deck is still aces. A diamond and then a diamond, well, 1/4 of the deck is diamonds. We return that diamond, so 1/4 of the deck is still diamonds for the second pull. If 2 events are independent, that means if one event does not affect the other, and certainly replacing the cards between pulls is a way to ensure that happens, we just multiply those probabilities together. Now, 2 cards without replacement. That means that we are no longer returning the card to the deck. It means we're keeping it in a sense. We've got it and we want to get another one. And notice that this notation is still the same. We still say and. We might say and then without replacement, but that becomes a little bit unwieldy. So we simply know the context that we're in. Now I'm going to use 50 seconds here just because the denominator is going to change. If we're not returning a card to the deck, then we no longer have 52 cards for the second pull. So in the first, there are 4 aces out of 52, exactly what you'd expect. We're multiplying exactly as you'd expect. But now we've got an issue. There are certainly 4 9s, but there aren't 52 cards. So the chance of pulling a 9 actually increased because the chance of pulling an ace decreased. We kept that first ace. So the chance of pulling that 9 as the second card without replacement reduces to 4 out of 51. And this is a job for a calculator. You can do this as an exercise in an arithmetic class, but I think it's perfectly fine to use the simplifier in your calculator and rewrite that as 4 out of 663. Again, without replacement, we're going to draw a diamond. There are 13 diamonds in the deck, so the first pull is exactly what you'd expect. 13 out of 52. Let's see that 52. The club, well, there are 13 clubs, so the numerator is definitely 13. The problem is that we kept the diamond. We didn't return it to the deck. So 13, but not out of 52, out of 51. And when we simplify this, we get 13 out of 204. The simplified fraction version gives us the exact answer. MyOpenMath is sometimes looking for the exact answer, so make sure that you've got that. If they're looking for a decimal, then you just use the division key instead of the fraction key in your calculator, and you get a decimal out, rounded to the correct number of places. A club and then a heart, and you say to yourself, didn't we just do this with a diamond and a club? And you're exactly right. We did indeed just do this. There are 13 clubs out of 52. There are 13 hearts, but now out of 51. A jack and an 8, and you say, well, that looks familiar too. That looks like that first question, the ace and the 9. And you're exactly right. A jack, there are 4 of them out of 52. There are 4 8s, but no longer out of 52 cards, now out of 51 cards, and we've seen the 4 out of 663 before. We can now ask a kind of silly question. What's the probability of getting an ace and then another ace? But this becomes a little bit more interesting. I shouldn't have said silly. This is actually a very interesting question in the sense that when we pull out that ace, there's 4 of them out of 52 to begin with. But now, not only are there only 51 cards left, there's only 3 aces left. Both the numerator and the denominator change. So this is, in fact, a new look. Make sure that you can see that both the numerator, the 4 became a 3, and the denominator, the 2 became a 51. Both changed because we're pulling out both an ace and just any old card. A diamond and then another diamond without replacement. Well, there are 13 diamonds, but we can write that as 13 over 52 because that's our first pull. The second card we pull out, well, there are only 12 diamonds left, so our numerator is 12, but our denominators also change, just like in the previous questions. There's 1 less card. And so 12 out of 51, we put this into our calculator and we get 1/17. So finishing this up, when 2 events are not independent, that simply means that one affects the other. So the moment that we say we're interested in event A happening, we want to know the probability that event A happened. We can't simply multiply that by the probability of B happening because it's changed because A happens. And that's exactly the way we write a conditional probability question. Notice that A and B is commutative, which means that we could just as easily say B and A, which means that we could write the probability of B times the probability of A given that B has happened. Now these are easy to remember the moment you think of them dynamically. I mean, that is over time. So I think of this as first the probability of A happens, and then B happens, but its probability has been affected by A. Similarly, if B happened first, then we'd say the probability of B, and then A happens, but its probability is affected by B happening. And if you're asking yourself, why is that? The answer is fairly straightforward. Multiplication is commutative. In other words, when I'm looking at any of these questions, I can change the order of the denominators, change the order of what I'm thinking about, and it doesn't affect the product or the quotient. Let's compare that with the rule when 2 events are independent. When they're independent, we don't have to consider that one affected the other. We simply multiply the probability of A times the probability of B. When they are not independent, we have to use conditional probability. So this is probably a good point to summarize our rules, because now we're going to use them. In other words, we're going to use them in a kind of arithmetic but algebra-looking setting. So the probability rules. If two events are mutually exclusive, then the probability of A or B is the probability of A plus the probability of B. And by definition, no real new information here. If you know they're mutually exclusive, they don't happen together. The probability of A and B happening together is 0. If they are not mutually exclusive, that is, that they could happen together, this doesn't promise that they will, but they could happen together, then clearly we add the probability of A to the probability of B, but we've counted twice. If they can happen together, then part of what we're interested in B has happened in A and vice versa, so we have to subtract that overlap. That means that the probability of A and B is not 0. Independent means that one event happening does not affect the other. So if I ask what's the probability of both events happening, it's simply the probability of one times the probability of the other. And that means that knowing that B has happened, as in this first statement, the probability of A given B, does not affect the probability of A. So knowing that B happened does not change the probability of A. Similarly, knowing that A has happened does not change the probability of B. It's still just the probability of B. If two events are not independent, then we say that the probability is affected. So knowing that A has happened affects the probability that B happens. So the probability of A times the probability of B given A. And since and is commutative, we could just as easily say the probability of B times the probability of A given B. Now, those last two statements can be made into equations solved for the conditional probabilities, and we do that simply by isolating the conditional probabilities. Now, we've got a lot of equations here, and equations can be used to answer questions. So let's get about doing that. This says, find the probability that a randomly chosen Californian has a college degree and is a Sacramentan, given that. And then it tells us a bunch of stuff. It tells us that 30% of Californians have a college degree. 9% of Californians are from Sacramento. And 35% of Sacramentans have a college degree. What we're interested in is choosing a Californian and finding the probability that that Californian has a college degree and is a Sacramentan. So the probability of D and S. So let's go through and see what we've got and try to figure out how to make that into what we want. So it says that 9% of Californians are Sacramentans. Let's use S to denote being a Sacramentan. So the probability of being a Sacramentan among Californians is 9%. Now notice that this entire problem is given that we're talking about Californians. So we don't actually have to use that. The entire problem, every number in it, is a conditional probability question, if you will, given a Californian. So we're simply going to say, well, that's our universal set, and go for it. The probability of having a college degree in California is 30%, so the probability of D is 30%. And the probability that if you've got a Sacramentan, that Sacramentan has a degree, so the probability of having a randomly selected Californian with a college degree, given that they're a Sacramentan, is 35%. And we're interested in finding the probability that a randomly selected Californian has a college degree and is a Sacramentan. So how are we going to do this? We want the probability of D and S, and we've got some conditional probabilities. So let's go back up here and look at our equations that combine ands with conditional probabilities. So let's see what we've got. So we might say the probability of D and S, which is what we're interested in, is the probability of D times the probability of S given D. So let's take a look at that. That's certainly what we want to find, and we certainly have the probability of finding someone with a college degree. What we do not have is the probability of S given D. We have the probability of D given S. So we cannot use this one. This one does not work for us without a bunch of extra work. So instead, we're going to say, well, maybe there's a better way to know that, to do this. So we don't know the probability of S given D. So instead, we're going to use the formula that's very similar, but starts off with the probability of S, and then says find the probability of D given S. So just using that commutative property. So when we plug in those numbers, we see that the probability of being a sacramentan is 9%. So taking the place of P of S is 9% as a decimal. And the probability of D given S is 35%. So we plug that in and multiply those two together, and we get 3.15% or 0.0315. So another very similar question. Here we just have events A and B. We're told that they're not independent. We actually didn't have to be told that. And the reason is we're also told that the probability of A and B equals 0.16. In other words, it's not 0. That means these events are clearly not independent. So make sure you can see that. Such that the probability of B given A is known, and we're asked to find the probability of A. When we look back through that list of equations that we've got, we're looking for something that combines our knowns. So we want something that has the probability of A and B in it, something that has the probability of B given A in it. And we do find such a thing. We find that the probability of B given A is the probability of A and B over the probability of A. And I should have mentioned that that's what we're looking for. So this equation helps us in one go. It gets us exactly where we're going. So we've got the correct equation. And you could plug in the numbers at this point and simply do some arithmetic. It looks like algebra. But we might as well just solve this for the probability of A. That means multiplying both sides by the probability of A to get it out of that denominator so we can actually work with it. We want the probability of B given A to go away from the left side, so we divide both sides by the probability of B given A. And now we've got our formula. It says that if you're interested in finding the probability of A, as we are, you first take the probability of A and B, and you divide that by the probability of B given A. So we're going to go through and we're going to do exactly that, plugging in what we know. If you simplify 0.16 divided by 0.45 in your calculator, you're going to get the kind of comical solution in exact form, 16/45. In other words, just multiplying numerator and denominator by 100. If you need a decimal approximation for that, you can use the division key. This last example is a little bit more complicated because this is asking us for something that isn't in the same formula with the thing that we're interested in. And even more interesting is the fact that we're given some negations here, some nots. So let's deal with those first. We're told that the probability of not A and B is 0.59. So we can use that information to find the probability of A given B. That's simply the complement. The probability of A given B is 1 minus 0.59, which is 0.41. So that's giving us the probability of A given B. Now, if you're wondering why I'm doing this, I'm hoping this will work because of where we're trying to get to. We're trying to get to the probability of A and B. There's no knots there. There's no knot on the A, there's no knot on the B, so we're simply getting rid of those negations first. So let's take a look at the other negation, the probability of not B. Since the probability of not B is 0.27, the probability of B is its complement. That is 1 minus 0.27, and when you do that arithmetic, you get 0.73. In other words, they add to 1. So now we've got the probability of A given B, and we've got the probability of B. So we're in great shape. we now need to find an equation that will give us the probability of A and B given what we've got. And we can find that relatively quickly. That comes from the probability of A and B equals the probability of B times the probability of A given B. Now we use that formula. We plug in what we know, we do the multiplication, and out pops 0.2993. Similar question, we are given the probability of A and B, the probability of A or B, and the probability of B. So we look through our formulas and we see that the formula for the probability of A or B has all these parts in it. It's exactly what we want. The probability of A or B is the probability of A plus the probability of B minus the probability of that overlap. So we're going to solve this for what we're interested in. We're interested in the probability of A. That means that two things have to go. The probability of B has to go. It's attached by addition, undone with subtraction. We're going to subtract the probability of B from both sides. So on the left side, the probability of A or B, and then we're going to subtract the probability of B from both sides to get rid of it from the right side so that the probability of A is by itself. But there is another thing we have to get rid of. We have to get rid of the probability of A and B. The probability of A and B is attached by subtraction, undone with addition, so we're going to add that to both sides. So on the left side, we'll add the probability of A and B. When we do that, we'll get the probability of A. So now this is a simple enough matter. We plug in the three things we know. The probability of A is the probability of A or B. The probability of A or B was given to us in the problem itself, and that is 0.58. So we're going to replace the probability of A or B, or substitute it with 0.58. The probability of B is known to be 0.3. So we're then going to subtract the probability of B. So we're subtracting 0.3. And finally, we are adding the probability of A and B, which is 0.16. So we'll add that 0.16 to the calculator as well. Press enter, and out pops 0.44. This last question will, at least the way that I found a way through this, I had to do two different equations. You might be able to find a quicker one, but I was just thinking along the lines of the previous problem. So we're told that they're not independent. We didn't really need to be told that because I see that the probability of A and B is not 0. So that's interesting information, certainly warns me which equations to use, but I didn't really need to be told that events A and B are not independent because 12% of the time they both happen simultaneously. We're asked to find the probability of A given B, and the hint, sometimes hints are great, sometimes hints force a student to do something in the same kind of awkward way that the professor did. If you can find a simpler way to do this, more power to you. So I'm interested in finding the probability of B first. So I say, well, how do I combine what we know, something about ands and A's and B's, to find the probability of B? And I know that I could find the probability of B using the formula for conditional probability. So we want to know what the probability of B is because we'd like to find the probability of A given B. So I'm just simply justifying my hint here. I'm saying if our goal is to find the probability of A given B, we might as well use the simplest formulation for it. That is the probability of A and B over the probability of B. But if you reread the question, you can see we've got a problem. We don't know what the probability of B is. So I'd love to use this formula, but I need to know what the probability of B is first. So now I ask myself, how do I use all this great stuff to find the probability of B? So I think to myself, well, the probability of an OR statement has an A, a B, and an A and a B in it. I've got the A and the B, so that would give me the probability of B. In other words, I've got everything in this equation except for the probability of B. So pause that and convince yourself that that's true. And let's go through and solve this for the probability of B. That means that the probability of A has to go. It's attached by addition, undone with subtraction. And the probability of A and B has to go. It's attached with subtraction, undone with addition. So do a little algebra, and we've got an equation for the probability of B. Now, that tells us to substitute in the probability of A or B, then subtract the probability of A, and then add the probability of A and B. When we do that, we get 0.41 in our calculator. Now we can go back to that very first statement. We'd like to use this formula because we'd like to find the probability of A given B. At that point, we didn't know what the probability of B was. We certainly do now. So we're plugging it in. So we're going to say that the probability of A given B is exactly that formula above, the probability of A and B, which we've known from the beginning to be 0.12, over the probability of B, which we just learned is 0.41. We do that division. We round to 4 decimal places. That's my default. The problem in my open math may ask you to do something different. Got a nice long decimal there, 0.2927. Interesting the extent to which you can use algebra in a stats class, and also indicative of Bayesian probability in its entirety. The idea that if you know one thing in it, or if you only don't know one thing in an equation, you can find it by plugging in everything else, and you can step through this process. It's kind of fun. I hope you enjoyed that. Okay, the next handout is a bridge. It's a segue from probability in a single context of how many ways can you do something to a much more general setting of counting. So this begins a whole new discussion of combinations and permutations. But I wanted to start with a fairly simple question of how many different wardrobes can you make out of 3 pairs of shoes, 8 shorts, and 2 pairs of jeans. And you might say, well, that's independent. Your choice of shoes does not affect your choice of shirts or your choice of jeans. So this is a simple enough matter of 3 choices. And for each of those 3 choices, there's 8 choices. And for each of those 3 times 8 choices, there's 2 more choices. So 48 different possible outfits. Similarly, if you ignore the fact that some license plates might spell out or look like weird words, and you are in a state where you have a digit followed by 2 letters followed by 2 digits, you might simply say, and you'd be correct, there's 10 digits, there's 26 letters, and multiply those across. There is a little bit more than 500,000, and I say a little bit relatively there, 676,000 different license plates. This is the way license plates look in California when I was a kid. Permutations and combinations are counting. They ask how many ways you can arrange things. These are the formulas, and they're useful up to a point. The weird thing about these formulas, they're great to think about what a permutation and combination is, to keep them separate in your head. But if you put this into your calculator, that exclamation point, you will actually get arithmetic overflow. Your calculator won't be able to do it. So instead, it's much more useful for the questions that we're going to see in our homework and on exams to use the stats menu and actually pull up the command for permutations and combinations. So here they are, and you can see at a glance that they are very similar. The only difference is that a combination has an r factorial in the denominator. So there are fewer combinations than there are permutations. And we're going to talk about why that is and how to keep them straight in your head. So here is the factorial. So if you see an n or a number followed by an exclamation point, that's read n factorial. It means to multiply all the integers down from that number down to 1. So 3 factorial is 3 times 2 times 1. N factorial is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. Factorials count the number of ways that you can arrange n things. All of them, all n things. So the question about combinations and permutations is a question of order. So when you ask yourself, I'm making lists of things, I'm counting things, you need to ask your question, does order matter? Okay, here we go. Both combinations and permutations count collections of R things, or people, or devices, or procedures, selected from among N things. So remember when I said N factorial counts the arrangements of N things? Well, that's assuming you use all N things. So when we're talking about combinations and permutations, we don't have to use all R things. We're only going to use R of those from among the N things. So in other words, there's 30 students in a class. We want a committee of 3 students. N is 30, R is 3. The difference is how these collections are considered. If order matters within the collection of R things or people, then we count the number of these collections, called permutations, with the P. Otherwise, when there is no order within the collections, we count the number of these collections, called combinations, with C. So I'm going to give you an example of that. And the mnemonic I'm going to give you is C for committees, P for president. So let's look at our examples. In how many ways can a president, vice president, and treasurer be elected at a school with 210 students? I'm going to show you how to do this with the permutation. It's a permutation because we have order. In other words, it's not just a group of 3 students. There's a president, a vice president, and a treasurer. So the idea that there's order in this group, it matters whether you're the president or the treasurer, tells us to use permutations. So from among those 210 students, we are choosing 3. We're using permutations. And when we do that, we get 9,129,120 ways. That's a fairly large number, even for a fairly small number of students. And that's largely because order matters in this question. You can imagine the Olympics and the different heights of pedestals that the athletes stand on when they're winning their prize. It matters to you which of those 3 you're standing on. Similarly, it matters whether you were elected president or vice president or treasurer. So because of that, order matters. We're not simply filling 3 spots, but we're filling them in the order president, vice president, treasurer. Notice that you could get this number another way. You could say that there are 210 choices for president, 209 choices for vice president, because you can't hold both offices, and similarly 208 choices for treasurer. And if you multiply those together, you get exactly the same number. Now, intentionally, a very similar question. This is the same school, and there's still 210 students. We've now moved on from the officers, and we're simply forming a committee, which could include the 3 officers, so we're talking about all 210 students. Now, something different happens. Now, with a committee, it doesn't matter whether you were the first one assigned to the committee or the last one assigned to the committee, except perhaps for your ego. You're just a group of 3 people assigned to look at a particular task. So in this case, C for committee, if you can imagine that what you're looking at feels like a committee with no order within it, then you're going to use combinations. So here, instead of a P, we're going to look at 210 C3. We're going to put that in our calculator and get 1,521,520. So much smaller. Remember, we got over 9 million in the previous question. This next question is slightly ambiguous, at least to me. When I am asked how many different seasons are there, I might think to myself, well, that's a little ambiguous. Does order matter in a season? And so I then look at the next question, and I can see what this question is asking. Once the 5 plays are chosen, how many different orders are there? So in other words, the seasons, the plays that are chosen in the season, we're assuming that that doesn't have order in it yet. So going back to question number 5, we're choosing seasons. There's 19 different plays available, and that might mean because of the length of the play, that might mean because of the number of players, it might be because of the sets that are available, the costumes that are available, all sorts of stuff. So 19 different plays are available, and we're going to choose 5 of those. So by looking at the next question, we can see that order does not yet matter. So this is like a committee. We're just choosing 5 out of 19, but we haven't put them in order yet. So 19C5 gives us 11,628. This question says, once the 5 plays are chosen, we've got 5 plays, we want to know how many different ways there are to put them in order. So we've got 5 choices for the first play, 4 choices for the second play, you see where this is going, 3 choices for the next, 2 for the one after that, and then we're all out of plays. We're not going to re-screen a play. We're going to use that last play. Well, that's 5 times 4 times 3 times 2 times 1, which is exactly 5 factorial. Now, if that feels to you like it kind of came out of nowhere and that I haven't been using the factorials, I've been using combinations and permutations, I agree with you. So I want to point out that this is exactly what you'd expect. So we're interested in putting 5 things, all 5 things, in order. So a permutation, so from the 5, we're choosing 5p5, and if you put that in your calculator, you'll get exactly the same number, 120. Now that's great when we've got permutations and combinations and we can imagine president, vice president, and treasurer, in which case we're going to say P stands for permutations, or it's great when you can imagine that order doesn't matter, and so you can think to yourself, okay, so that's like a committee, and a committee is a combination. P's goes with P's and C's go with C's. But let's talk about some other situations just to make sure that we're all on the same page. If I'm choosing passwords, that is a permutation. Passwords order matters. I think we all know that. I only recently learned this. If you choose lotto numbers, the order in which you choose them doesn't matter. So that's a combination. If you have different offices, if the order matters in which you're putting different people in different offices, then that's a permutation. Of course, committees, that's a combination. If you care about selecting some zip codes and you care about the order in which you visit those zip codes, then of course order matters. That's a permutation. If you don't have to worry about actually traveling there, you're going to send those surveys, then it's just a unordered list. You'd use combinations. If you have different presents and you're thinking, well, who should receive this present and who should receive that present, then that's a permutation. If you have a box of greeting cards and they're all the same and you just want to figure out who you're going to send it to, that's like a committee, that's a combination. If you want to figure out who is going to go to bat and in what order, order tells us it's a permutation. If you're simply choosing who's going to get to go to bat, that's a combination. If you are putting pianists in order for a recital, then that is a permutation. If you're simply choosing which pianists get to play, that's a combination. At this point, you're kind of bored because these all have similar characteristics and you can probably identify them pretty quickly. So let's look at arrangements of things, and this becomes essential in the next chapter. So arranging different things, that's a permutation. Arranging identical things, that is a combination. And that's also the subject of the next page. So what is an arrangement? If I have 8 places, and I've illustrated that with what I hope looks to you like 8 little trays or 8 little pots or 8 little places you can put something, kind of placeholders. So here is 8 places. And in those 8 places, we are going to arrange exactly 3 ones. So this is what we mean about an arrangement. So those ones could be in the 1st, 2nd, and 3rd place, the 6th, 7th, and 8th place are scattered about. But ones are all identical. So if you remember the previous page, you can already answer this question, but I want to go through this in a little bit more detail as well. So let's think about where the ones go based on their position. So let's look at this little tray, or this set of 8 trays, and let's give each a number, and let's say that the position numbers are 1 through 8. So we're going to choose where ones go, and we're going to choose that by choosing 3 position numbers. So in that collection, that list, we're going to select 3 locations to put ones. So we could select 1, 2, 3. And put 1s there and 0s everywhere else. These are binary numbers. They're either 0 or 1. That would give us the binary number 111, 000000. Similarly, we could choose 213, and that would mean it would place 1s in the first position, the first 3 positions. And again, we'd have 111 followed by zeros. So notice that order does not matter here. We're arranging identical things. All 1s are considered to be identical to other 1s. So this quickly becomes a combination question. 8 places, 8 position numbers, and we're choosing 3 of those where order does not matter. So if we're arranging identical things, order doesn't matter, and we use combinations. In the next question, we're asking how many ways can it rain on 3 different days in a week. So a week is 7 days. And if you're imagining a calendar, we're going to put R's in 3 of those for rain. And then the rest are not going to have R's. A rainy day is considered, at least in this question, we're assuming that a rainy day is considered equivalent to another rainy day. So we're simply going to find out how many arrangements of identical things we can have here. So again, a combination from 7 days in the week. From 7 squares on a calendar, we're going to put R's in 3 of them. The next question says, how many ways can 3 deluxe model homes and 5 standard model homes be arranged on a demonstration block? All 3 of the deluxe model homes are considered to be identical to each other. So we're finding the location of those 3. Once we find the location of those 3, the other locations are simply filled with the standard model homes. We don't need to focus on the other one, just on the fact that together there are 8. There are 8, and we're finding where 3 of those go. So 8, choose 3. And at this point you say, well, maybe these are always combinations, but let's take a look at this last question. So you're giving your pet some birthday presents. You can see what I think about. And there's 3 different gifts, a bone, a new collar, and a ball. All of these things my dog gets without it necessarily being her birthday. Lots of bones, lots of chewy stuff. But 3 different things. So we're not simply saying arranging gifts, we're arranging different gifts. So this is unlike the previous examples in the sense that we are arranging different things. So in a sense, order matters. In a sense here, the bone one day, the collar another, all this stuff, the order in which it happens matters. So instead of a combination, this is a permutation. We're looking at a week again, so from those 7 days, we're ordering 3 among them. Notice that we have on the screen right now 7 choose 3 from the combinations, and we also have 7p3 from the permutations. And you can see that when order matters, there are a lot more ways of arranging things. And I'm going to quickly go back to that previous page, and I am going to highlight arranging different things is a permutation. Arranging identical things is a combination. So now that we have seen examples of what an arrangement is, then I'm pointing out that the differences here is between different things and identical things. Identical things like 1s and deluxe houses are combinations. Different things like different presents are permutations. And all of that is in many ways a preamble to what's coming in the next chapter. We are using combinations. We're going to count the number of ways. Remember, counting ties back into probability, because if we can count the number of ways that the desired event happens and divide that by the total number of ways something can happen, we've got ourselves a probability. So we're exactly headed towards a question like this. we're going to toss a coin 7 times. Now, one of the things that is easy to forget is that if you toss a coin 7 times, you might get 0 tails. We're counting tails on this question. So remember, there's 8 different possibilities when you toss a coin 7 times. And I did say that correctly. 0, 1, 2, all the way up to 7. You might get no heads at all. And so we might want to know the different numbers of ways that that can happen. Now, this is exactly where we are headed next semester, or excuse me, next chapter, in order to find the probability of tossing 7 heads, 3 heads, 0 heads. And the first thing that we need to do is we need to figure out the number of ways that that can happen. Now, tossing a head is considered identical to tossing another head. So we don't consider these different things, we consider these identical things, and the same for tails. A tail is the same as another tail. Now, another thing to point out is that it's possible to toss 0 tails. So if you look at that first row, when we're tossing exactly 0 tails, that can happen. But it only happens one way. And you can quickly see how. It only happens in the way that you've tossed all heads. And I'm going to point out some symmetry right now. We'll return to this at the end as well. Notice that there's only one way to toss exactly 7 tails, and that is if you have tossed no heads at all. There is only one way that that can happen. Now let's look at tossing 1 tail. Well, this one you don't really need a combination for either. You can simply say, well, it could be the first thing you toss, the second thing you toss, the third, fourth, fifth, sixth, or seventh. There's 7 ways you can arrange one toss of tails among 6 other tosses of heads. So it could be the first, second, third, could be the last. So that only has one way. Similarly, if I'm counting 6 tails, that means there was only 1 head. So in your head, just swap heads and tails, and that 6 row simply means 1 head. Well, that means the head could be the first, it could be the second, it could be the third, fourth, fifth, sixth, or seventh. Again, 7 possibilities. Now, the second, with 2 tails, we ask the question, what's 7 choose 2? We put that on our calculator, or we can compute it. None of these numbers are too big to run out our calculator's memory. We could use the definition involving factorials. On the previous page, we saw 7 choose 3. That was 35. And I'm going to point out the symmetry here. This message repeats. There's only 35 ways to arrange 4 things among 7. Well, that's the same as saying that we're only interested in counting the other 3 arrangements. So that symmetry is entirely built into combinations. In fact, the last time, or the first time that you saw this, was almost certainly called the binomial coefficient, when you're raising a binomial to a high power in Math 120 in an intermediate algebra class. And to get those coefficients on the powers of each of those terms, you used combinations. And that's exactly what's happening here. Now, the total is what you'd think. You add them all up. But it's something else as well. The total number of ways says that there's 2 outcomes, equally likely, 2 potential outcomes for the first toss of a coin. So that's 2. There's another 2 for the second toss. There's another 2, and I should be saying for each of those first 2 ways, there's 2 more ways. And for each of those 4 ways, there's 2 more ways. And for each of those 8 ways, there's 2 more ways. So 2 to the 7th means 2 times 2 times 2 times 2 times 2 times 2 times 2, and that's easily enough to calculate on your calculator, 128. If you want to pause this and actually do that arithmetic once and convince yourself that it adds up to 128, that's probably a good way of convincing yourself that these 2 ideas are connected. 2 to the 7th, a 2 multiplied by itself 7 times, because in each of those tosses, there's 2 potential outcomes. Now we're going to use this table to answer some questions. and kind of tie that back in. In how many ways can you toss a coin 7 times and have 3 tails? Tails are considered identical to each other, so this is a combination. There's 7 total, so 7 choose 3, and we see that we've calculated it again. That's exactly what we calculated in the table earlier. How many ways can you toss a coin 7 times and have 3 or 4 tails? Well, this is a little bit more interesting. We could compute these numbers again, or we could simply add 35 to 35. 7 choose 3 plus 7 choose 4 is 35 plus 35, which is 70. And that'll work for probability too when we get there. The complements of events are always useful, and we're going to tie that in here because this is a perfect way to introduce the next chapter. The number of ways that an event does not occur. So if I'm interested in something not happening, I can take all the ways that an event can happen, the total number of events that can happen, and I can subtract the number of ways that the event actually does happen. So if I am interested in something not happening, I can take the total and from it take away the number of that event actually happening. So let's look at a case like this. You can check by working through this, but we're asked what the number of ways that you can toss a coin 7 times and have less than 7 tails. What does that mean? That means when we go back up here, that means we're talking about everything. 0, 1, 2, 3, 4, 5, 6. Everything except that last case where we tossed 7 tails. So you look at this and you say, well, that's asking you to add up some numbers. It's not particularly difficult. 1 plus 7 plus 21 plus 35 plus 35 plus 21 plus 7. You could even use multiplication. But notice that what we're interested in here is everything, and I'm going to highlight the 128 when I say everything, but that is taking away the one case we don't want. So all that fancy rule says is if you are interested in finding when something does not happen, it might be simpler to take away when it does happen from everything. So let's go back down here, and we see that there are a total of 128 different ways you can toss a coin 7 times. One of those ways is the only one we're not interested in, when we've tossed it 7 times and got 7 tails. So we can simply do that subtraction. And if you've already added up those 6 numbers, you've already got 127. Okay, and for our very last question, we're generalizing these results, this idea of counting the number of ways that you can toss a coin, and this idea of the complement. So here we're tossing a coin 15 times, so that means there's 2 to the 15th power different ways that you can have heads and tails. And that's interesting to us because we're interested in having at most 14 tails. Well, at most 14 means we could have 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 14. It's really only preventing one situation, and that one situation is when we have exactly 15 tails. Well, 15 tails and 15 tosses happens only one way, so we're basically taking 1 from the total number of ways that you can toss a coin 15 times. So 2 to the 15th minus 1. 2 to the 15th, according to my calculator, is 32,768. And if you subtract 1, you get 32,767. That's a cool way to end this discussion of probability, is by looking forward to our discussion of binomial probabilities.